Hi, so today I will introduce you to our main contributions in the paper Improving the Performance of Heterogeneous Data Centers Through Redundancy. This is a joint work with Urzi Ayesta, Mathieu Jonker, and Maike Berloop. So the main topic of today is redundancy, which is a load balancing technique implemented in computer clusters. So the general notion of the redundancy is that upon arrival, each job is going to do several copies of itself and is going to dispatch these copies into several servers in the system. And then the job will wait until the first copy completes service, moment when the additional copies of the job are removed from the system, so that the job will experience the minimum response time among the response time of each copies. So in the end, redundancy aims to exploit the variability of the queue lengths and server capacities in order to minimize the response time of each jobs. So today we are going to have two main objectives. First, to characterize the stability condition and the redundancy model when servers implement processor sharing, and secondly, to compare the stability condition and the redundancy to that of a non-redundant system. And we are going to consider the Bernoulli routing system, where each job is going to dispatch one single copy to one of the servers among its compatible servers, choosing uniformly at random. So before we start with these objectives, we are going to first give a proper model description. We consider, in the end, a parallel server system under processor sharing, where each server has heterogeneous capacities μs. Jobs arrive according to a Poisson process of rate lambda and have generally distributed service times with unit mean. Under redundancy, the redundancy topology characterizes to which of the servers each job is going to dispatch its copies. So we are going to label each job with a type C that is given by the subset of servers to which the job is going to dispatch its copies. And then we are going to denote by capital C the set of all types, and a job is going to be of a type C with probability PC. So a well-known redundancy model is the redundancy D model, which is a homogeneous capacity server system under the redundancy D topology. So under this topology, each job is going to dispatch D copies into D out of K servers chosen uniformly at random. So in this example, we have a 3-server system under redundancy 2, and jobs are going to be of type 1, 2, 1, 3, and 2, 3. That is, a job can send copies to servers 1 and 2, or 1 and 3, or 2 and 3. The correlation structure among the copies characterizes how the copies of the same job are related among them. Two well-known structures are the IID copies and the identical copies. Under IID copies, every copy of a job is going to sample an independent and identically distributed service time according to the service time distribution of the original job. And under identical copies of the job, all the copies of a job will have the same size as the original one. So, the challenge of analyzing redundancy models comes from the departure process of the system. As I said before, each job is going to depart only when one of the copies completes service. And in that moment, all the additional copies of the job that are still in service are going to be removed. So then if we look to one of the servers, we are going to have a departure due to one of the following events. So on the one hand, there is a copy that completes service in these servers, and on the other hand, in this server, we are going to find a copy of a job that has completed service in some other servers. So in this example, if the orange job leaves the system first in server 3, then server 2 is going to have the departure also of the orange job, even if this copy didn't complete service yet. So Now I will show which are the stability results that are known already in literature for the redundancy models with processor sharing. First, under exponentially distributed service time and IIT copies, in a previous work we have characterized the stability condition for the redundancy D model. And we show that this is given by lambda needs to be smaller than k times mu. We observe that this is independent of the number of copies in the system, and that is also the maximum stability condition that one can obtain under exponentially distributed service time. We show also that when copies are instead identical copies, this stability condition reduces to lambda needs to be smaller than k times mu divided by d. And you observe that this coincides with the stability condition of a system where all the copies need to be served. And also that the stability condition decreases in the number of copies d. Remakers et al. Generalize this stability condition to generally distributed service times and also give a necessary stability condition for the generally correlated copies, which is given by lambda times d, and the expected value of the minimum among the service time of the copies of one job needs to be smaller than k times mu. So within this talk, we are going to consider the system under generally distributed service time and identical copies, but for the general redundancy topology. And we are going to characterize the stability condition as a set of conditions that is obtained by an algorithm that we are going to describe. And we will see that this algorithm reduces, in the case of the redundancy D model, to also this stability condition. So let's start by obtaining the stability condition in this case. To do so, we are going to first analyze an example of the trajectory of the number of copies per server in order to have some intuition in the stability condition. We have a 4-server system with heterogeneous capacities, and where each job is going to dispatch the 2 copies with some probabilities. And then lambda is going to be 7.5. In this figure, we plot the number of copies per server within time for servers 1, 2, 3, and 4. And we observe that eventually all the servers are going to get empty. But now we are going to analyze how this happens. So first, we consider server 4, which is the server that empties first and stays empty for the rest of the time. When we compute the load in this server, so it's lambda times the fraction of arrival that arrives to server 4 divided by the capacity of the server, we have that this is smaller than 1. And if we ever compute the load in the rest of the servers, we are going to obtain that these loads are not smaller than 1. Next, we are going to observe the system after the time where server 4 is empty. And we can consider that this is a 3-server system with jobs of type only 1, 2, 1, 3, and 2, 3. So we have this subset of the system. And here we observe that server 3 is the next server that gets empty. Meanwhile, the trajectory of the servers 2 and 1 are still or increasing or decreasing. So if we compute the load in this server in the subsystem only composed by servers 1, 2, and 3, we have that this is lambda times the fraction of jobs that go to server 3 composed by the jobs of type 1, 2, 1, 3, and 2, 3 divided by the capacity of the server, and this is smaller than 1. And if we also compute the load in servers 2 and 1, we will observe that this is not smaller than 1. But let's see what happens after the time where server 3 and server 4 get empty. You observe that now, and only now, the trajectory in server 2 and 1 is decreasing, and that eventually these servers will get empty. So now, after the time where server 3 and 4 get empty, we can consider, or we can see the system as a two-server system composed of server 1 and 2, where there is only jobs of type 1, 2. And when we compute the load in server 2, we are going to observe that this load is going to be decreasing, is going to be smaller than 1. So now we are going to observe how we characterize the stability condition that it is recursively. So first we need to compute the load in each of the servers, and we are going to consider the minimum load. And this needs to be smaller than 1. So then we are going to call by L1 the set of servers for which minimum load in system S. And we are going to construct system S2, which is composed by all the servers except the ones that have the least load in the system. Next, we are going to compute the load in each of the servers in the subsystem S2. That is lambda times the fraction of arrival that arrives to each of the servers, and are also in the subsystem S2 divided by the capacity of the server. And this load, the minimum load in this subsystem, needs to be smaller than 1. And then we call by L2 the set of servers with least load in the subsystem S2. And then we create a subsystem S3 composed by the servers in S2 except the ones that have the minimum load in this subsystem. And so on until there are no more job types to assign. So in the last subsystem, it's going to be composed with the servers that are least loaded in the SE star subsystem, and for the SE star plus 1 there are no more job types in the subsystem, so we stop there. So in the end, the stability condition is going to be characterized by the following set of conditions. For every subsystem, every server with the minimum load in this subsystem, the arrival rate to that server, which is given by lambda times the fraction of arrivals that go to this server and are also in the corresponding subsystem, needs to be smaller than the capacity of the server. We note that this stability condition coincides with that of a system where each job dispatches copies to each least loader servers. And now we are going to analyze what happens for the redundancy D model. To do so, we have the following example that is a 4-server system and the redundancy D. So the probability of a job type is 1 divided by 6, and the arrival rate to a server is going to be 4, because there are 4 job types that arrive to each server, so 4 divided by 6. We have homogeneous servers, and lambda is equal to 1.8. So in this figure, we have the number of copies per server within time for the different servers, and we observe that all of them from the beginning have a negative trajectory and get empty. So if we compute the load in the servers, we have that this load is equal for all the servers and that this is smaller than 1. So then from the algorithm, we are going to characterize that L1 is going to be the set of all servers. And then the stability condition reduces to lambda needs to be smaller than k times mu divided by d, which is a stability condition also obtained in the following paper from ours. And we note that this stability condition coincides with that of a system where all the copies need to be served and is decreasing in the number of copies D. So now we are going to keep with the second objective of the talk, that was to characterize or to analyze when the stability condition and the redundancy is larger than that of a non-redundant system. And as non-redundant system, we consider the Bernoulli routine system. So here, each job is going to dispatch one single copy to one of the compatible servers chosen uniformly at random. So then we can see this system as a k-independent server system when the arrival rate to each of the servers is characterized by the sum of all the fraction of types that the server can serve divided by the cardinal of the type for all the types that are served in the system. And we have that the stability condition is characterized by the maximum load in these servers. Then we call by lambda R the stability condition under redundancy, which is given by the maximum load among the different stability conditions that we obtained before. And now we are interested in analyzing when the stability condition under redundancy is larger than that under Bernoulli routing. And to do so, we are going to look to the following example. We consider the redundancy D model with heterogeneous capacities, where the capacity of a server K is mu to the power of K minus 1. We compute the stability condition for redundancy 2 and redundancy 3 for different number of servers, also for the Bernoulli routing system, and for different values of mu. We note that when mu is equal to 1, this is just the redundancy D model, for which the stability condition under redundancy is mu times K divided by D, and the stability condition under Bernoulli's routing is mu times K, so that the stability condition under Bernoulli routing is always larger than under redundancy. Now, in gray, we observe the values for which the stability condition is again larger under Bernoulli routing than under redundancy. The mu star value is an approximative value for which both stability condition coincides, and then the white values are the values for which the stability condition under redundancy is larger than that under Bernoulli routing. So we have three main conclusions from this table. So first, for a given number of servers copies D, so for example redundancy 2, we observe that the value mu star decreases as the number of servers K increases. So this means that as the number of servers increases, the heterogeneity that is needed so that the stability condition under redundancy is larger than under Bernoulli routing is going to decrease. Now, if we fix a number of servers K, for example, K equal to 4, we observe that the mu star value is going to increase as the number of servers increases. That means that for a fixed D, as the number of for a fixed K, as the number of copies D increases, we need more heterogeneity in the server so that the stability under redundancy is going to increase compared to the Bernoulli routing. And now we are going to look to the values in bold, and we observe that for a fixed K, here the stability condition under D is going to increase. So here, if we consider K equal to 10, we observe that the stability condition under redundancy 3 is larger than under redundancy 2. And this was in contradiction to what we obtained before, that when server capacities are homogeneous, the stability condition reduces in D. So, which are the main conclusions of our talk? First, that the stability condition under processor sharing is characterized by that of a system where each job only dispatches copies to each least loader servers, and secondly, that when server capacities are sufficiently heterogeneous, the stability condition can considerably improve compared to that of a non-redundant system. So in the end, what we have done is to characterize the stability condition for the general redundancy model topology with identical copies and generally distributed copies. So the table of the stability conditions under processor sharing is going to be like this. Now, we are going to provide a conjecture for the case of the exponentially distributed service time with IID copies and the general redundancy structure. We have that for any work conserving policy with non-preferential scheduling policy, including processor sharing, the system under these conditions, so IID copies and exponentially distributed service time, if it's stable if for all the subset of types, the arrival rate to this subset is smaller than the sum of the capacities that can serve these job types. We know that this stability condition is independent, is the maximum stability condition that one can obtain under exponentially distributed service time. To see more open problems and conjectures on redundancy and other scheduling policies, you can go to this paper of ours where we discuss these features. And that was it. Thank you for your attention.